Hello and welcome. In this video, we're going to be taking a look at surfaces in 3 dimensions. Now, we've seen surfaces before of the form where z equals a function f of x, y. That certainly gives us a function, but it's not necessarily going to be the most interesting function. Since that has to be a one-to-one function, for every x and y that we plug in, we're only going to get a single value of z. But what we're going to be looking at now is a parametric set of equations for x, y, and z in terms of some parameters. And that can get us quite an interesting type of surface. So let's start off with the fact that when we're looking at a surface, we're going to need two parameters. From sort of an intuition, we can think about the example where we do start off with a function z equals f of x, y. Well, in that case, you could think about x and y as basically being our parameters, and z being just a function of those two. Now remember that we have some kind of domain for x and y. X and y would belong to some sort of set D. Now those are two variables, so D would be a subset of R2. If you want to try to represent that visually, then we can imagine that that domain D is just some region on the xy plane. And for every single point there in the region, when we plug that value of xy into our function, we get some value of z. And we plot that point at the point xyz. And that gives us some sort of surface in a third dimension then. All right, well now let's expand upon that. And instead of having x and y as being our variables or our parameters, let's choose two other variables such as u and v, and then we'll let x, y, and z all be functions of those two parameters. If we have u and v as our parameters, then we could say that x is some function f of u and v, y is a function g of u and v, and z is a function h of u and v. And u and v, again, will have some sort of domain. It'll be a domain D that is a subset of R2 since we have two variables. Now, in this case, that domain is not necessarily the x and y plane anymore. This is going to be a plane that is having the axes u and v, and that gets us a point x, y, z in three-dimensional space. So our parameter domain here would just be a region D existing on the uv plane. And every point in that domain is going to be mapped to a three-dimensional point in R3. And it's the mapping of all of the points in D onto those mappings F, G, and H that gives us this surface. Now, perhaps the easiest example of a surface would just be a plane in R3. And we know how to represent a plane using z equals f of x, y. And that's good for any plane except in the case where we have a vertical plane. If we want to expand the idea and parameterize a plane of any kind in R3, we can express that in parametric form by just having two vectors that exist in the plane. Let's start off with a couple pieces of required information. We'll need a point, x naught, y naught, z naught, and two vectors that are contained in the plane. Let's say that those are a and b with the components a1, a2, a3, and b1, b2, b3. Then a plane is simply just all of the points that are spanned by A and B, some sort of linear combination of A and B that would start from that point x naught, y naught, z naught. So let's say R is the position vector of any point on that plane. Well, then that would simply be equal to the position vector x naught, y naught, z naught plus a linear combination of A and B. So why don't we use u and v as our scalar multiples of the vectors A and B? Well, that right away gives us a set of equations for x, y, and z. We would have x equals x naught plus ua1 plus vb1, and y equal y naught plus ua2 plus vb2, and z equals z naught plus ua3 plus vb3. And if we wanted an infinite plane, then we would just have u and v belong to the set R2. If we wanted a half a plane, then maybe we could just say that u needs to be greater than or equal to 0, and we could simply make that a half plane, for instance. Of course, we could also just keep this in our general vector form. In that generalized vector form, r equal r naught plus ua plus vb, where a and b are vectors, might be an easy way to remember how to find the parameterization of a plane. All right, well, now that we know how to construct a plane, why don't we start looking at a slightly more interesting object? Let's take a look at maybe some kind of cylinder. Now, when we think about a cylinder, we often think about the case where we have a circular cylinder and a right circular cylinder at that. To construct a circular cylinder, we could start off with a circle such as x squared plus y squared equals 9. Now, on its own, if we don't mention z, then we would all maybe imagine that it's just simply the equation of a circle on the xy plane centered at the origin with radius 3. But the moment that we want to make that a cylinder, we have to also kind of give this extra information. We want to also specify that z could be anything. The moment we bring that third dimension in there, then we have a set of points where z can be anything, but x and y must obey this equation defining a circle. Well, on its own, it's not the greatest way of trying to represent a cylinder. Why don't we actually give that in a parametric form? We're certainly better off to try to maybe take that circle and change it into polar coordinates. And so we could say x equals 3 cosine theta and y equals 3 sine theta. And that actually would just simply be the parameterization of a circle in R2, where theta is our parameter. But now we're going to add an extra parameter into this equation to allow z to be anything. Z gets its own parameter. We could say z equals z, that would be fine. But if you don't like having z equals z, then just choose some other parameter, maybe just like u, for instance. Now we have the parameters u and theta, where u might be any real number, but theta we would want to have from 0 to 2 pi. Now that gets us a nice circular cylinder, but we can expand upon that. In fact, now that we can just let any variable equal some parameter, we can very quickly take this cylinder and make that circle on any of the coordinate planes and have the cylinder go along the z, y, or x axis. Another example of a circular cylinder with radius 3 would be just letting x equal u, y equal 3 cosine theta, and z equal 3 sine theta. Well, that would also be just another radius of 3, but this would be going along the x-axis. Now, we don't have to have just a circular cylinder. We can be a little bit more creative. Be a little bit more creative here. Why don't I do an example where I'll let y equal some parameter u. And x and z, I'm not going to use u at all. If I just use some other parameter for the functions for x and z, then I just essentially get a parametric equation for a line on the xz plane, and letting y equal u will turn that into a cylinder. Now here's kind of an interesting shape. Why don't I try letting x equal cosine cubed v and z equal sine cubed v? Now that's not going to be a circle anymore. Let's see what kind of a shape that ends up getting us. Luckily I've got Maple here to help us to see kind of what that shape actually looks like. Now here in Maple I'm going to make sure I have additional plotting tools so I can plot three-dimensional functions, and I've got that parameterization cosine cubed v, u, and sine cubed v, and I'm going to just plot this for u equal -2 to 2, and let's just choose to go around from 0 to 2 pi, since it kind of seems more intuitive when we have trigonometric functions. Let's see what we end up with. Sure enough, it's a cylinder. It's not a circular cylinder. You can see all of the cross sections are the same though. Every time I take a cross section along the xz plane, I'm always going to get this x equals cosine cubed v and z equals sine cubed v. And that is this interesting looking shape right here. Now that shape there of x equals cosine cubed v and z equals sine cubed v, that's actually called an asteroid. That's this little sort of diamond shaped pattern. But because we have a parameterization of a line in the xz plane and we have y being free, that suddenly turns this into a cylinder. I could simply just change this parameter domain and I end up with a longer cylinder. Now, of course, this isn't to scale, so there we go. It looks a little bit more like that now. We've got a perfect cylinder. So a cylinder is fairly easy to spot in parametric form because a cylinder is simply going to have a free variable. So that's going to be a single parameter for x, y, or z, and then we end up with the remaining variables, x and z, just being parameterized in terms of a single other parameter. Okay, well, let's take a look back at some other examples here. Another fairly common and simple shape would just be a sphere. Now let's take a look at a sphere of radius 4 centered at the origin. Now in Cartesian coordinates, We know that this is not a function. Z is not just a function of x and y, but we could write this as an equation, x squared plus y squared plus z squared equals 16, which is simply the radius squared. However, it does look a lot better when we convert this to spherical coordinates, since the distance from the origin is always going to be equal to 4, and the angle theta can be anything from 0 to 2 pi, and the angle from the z-axis phi can be anything from 0 to pi. This just becomes the equation rho equals 4. Now, rho equals 4, again, is a little misleading unless you also know that theta and phi are also variables. To make this a little less confusing, let's take a look at the conversion of spherical coordinates back to Cartesian coordinates and use our parameters theta and phi to express a parametric equation for this sphere. To get the z component is fairly straightforward. We're going to just simply take rho and multiply by cosine of phi. If we want to find the x and y coordinates, though, we're first going to have to take rho and multiply by sine of phi. And that is essentially converting from our spherical coordinates to polar coordinates, but then we continue to convert to x and y by multiplying by cosine theta and sine theta. Now, at this point in time, you can see we have x, y, and z equations in terms of our parameters phi and theta. And so once again, this is going to be a surface. Now, if we want to, we could also write this in vector form. And that would simply be those three components. Now, what if we wanted to just take the sphere and shift it slightly? Changing the radius would be fairly obvious. You can see changing 4 to 5 would be no problem. But this particular shift is also just about as easy as anything else. If we wanted to move the x coordinate, then we'll simply just shift x by adding on some value. So if we have a sphere of radius 5 centered at 2, -3, 5, then we'll simply take our parameterization from before. We can copy and paste that. We're simply going to change the radius to 5 and then apply a small little shift x, y, and z. Well, this is just already a sphere, but we want to add 2 to all of the x components. That we'll take all of our points and change x to x plus 2. And we're going to take all of our y components and shift them by -3. And we're going to take all of our z components and shift those by 5. So it's fairly intuitive. We're just simply making every of our original point x, y, z a new point by adding or subtracting a value from the three components. All right, now what if you're given a parameterization of a surface? It doesn't seem to follow one of these typical type of scenarios. What if we have a really bizarre looking surface? How are you going to be able to try to visualize that from its equations? Well, I recommend trying to use kind of like a grid strategy. Start off with the parameter domain, u and v, and then think about the grid lines of that two-dimensional domain. And each of those grid lines is a set of points that will exist on the surface. And maybe you can get an idea of what the grid lines look like on the surface in 3 dimensions. Going back to this picture of the parameter domain and the surface, well, I'm just going to add grid lines onto the parameter domain. And those are going to be running horizontally and vertically. Vertical lines there would be if u is constant. Horizontal lines would be if v is a constant. Now, on each of these lines, vertical or horizontal, we have a set of points. And each of those points we mapped onto the surface. So this vertical line, where u is a constant, is now going to be mapped to some sort of curve. And hopefully the curve, it will be somewhat familiar. Maybe if that curve is a circle, then you can see that all of these grid lines are sort of like cross sections that give us circles. Maybe that curve is a helix, and that'll give you an idea that the surface would have some kind of twist to it. And same thing with the horizontal line. If v is a constant, that is also going to get us some sort of curve along the surface, and those are going to be also some form of a grid line. Let's take a look at this surface where x is equal to 2 plus sine v cosine u, and y is equal to 2 plus sine v sine u. And z is going to be u plus cosine v. Now, u can be any real number, but v will simply just be from 0 to 2 pi. Let's take a look at what happens when we look at the grid lines on the uv plane and see how those become curves in R3. Let's start off with u being a constant. Well, if u is a constant, we can just maybe choose some convenient values of u and get an idea of shapes here. Let's start off with u equal 0, a nice easy value to plug in. If that's the case, then we'll end up with a curve, and we'll see if we can figure out what that curve would look like. X is going to be equal to 2 plus sine v. Y is going to be equal to 0, and z is going to be equal to cosine v. All right, now remember that v is from 0 to 2 pi. If we ignore this plus 2, we have x equals sine v and z equals cosine v, and we should recognize that as being a circle centered at the origin with radius 1. But if we put that 2 back in there, that'll give us the idea that it's simply a circle shifted along the x-axis by 2 units. So if we want to describe that, that'll be a circle of radius 1 on the xz plane centered at x comma z equals 2 comma 0. It might also help if you want to just quickly sketch that. Another convenient value to maybe plug in would be something like u equal to pi over 2. In that case, x is equal to 0. And that means that we're going to have a curve on the yz plane. That's going to help us to visualize this a little easier. Y is now going to equal 2 plus sine v, and z is going to equal pi over 2 plus cosine v. Once again, we have that typical sine v, cosine v. That's a circle on the yz plane. But now we've shifted it to y equals 2 and z equals pi over 2. Once again, we can draw a little picture of that. Now, in general, we want to really think about what this is always going to look like when u is any constant. So if we just let u equal u naught, it's important to know what is going to be a constant in each of these equations. 2 plus sine v cosine of u naught now. U naught is just a constant, and that's just going to get distributed across both of those terms. And the same thing goes with y. Sine of u naught is just a constant, and that'll get distributed across this 2 plus sine v. And z, well, that's always just going to be some sort of constant plus cosine v. And you can see how we may have that same kind of idea of a circle, but it's not going to be always a circle on the xz plane or yz plane. It's going to be a circle that is somewhat rotated. It might help to think about this actually in terms of polar coordinates. Using our idea of polar coordinates, we know that x squared plus y squared is equal to r squared. So if we actually were to use that conversion here, we took x squared and y squared, and we add those together, then we'll end up with sine squared u naught plus cosine squared u naught, all times a common factor of 2 plus sine v all squared. That means that x squared plus y squared is simply just going to be 2 plus sine v all squared. And if we square root that, we end up with r. So that tells us that r is equal to 2 plus sine v, and z is equal to u naught plus cosine v. So this is going to always be a circle on the rz plane. So it's going to give us a circle, and we're rotating that around with the parameter u, but we always end up with a circle. All of these grid lines are going to be circles spiraling around the z-axis. So essentially, by converting to cylindrical coordinates, we've seen all of these grid lines where u equals a constant are circles in the rz plane. Now, let's take a look and see about the other grid lines where v is some kind of constant. Now, it might help to just start off with an easy constant such as v equals 0. Taking a look back at the parameterization, if we let v equal 0, then x is 2 cosine u, y is 2 sine u, and z is equal to u. And let's remember that u is any real number. This is the parameterization of a helix. Now, oftentimes instead of u, we would have theta here, but no matter what we use as a parameter, it's still going to be the equation for a helix. And it depends on what we're also choosing for v. We can always choose a different value of v if we decide to maybe let v be another convenient number, such as pi over 2. Then we should get a similar helix. In this case, we'll end up with a helix with a radius of 3 and z equal u plus 1. So that's simply just been shifted up by 1, but with a bigger radius. Now, once again, it's always good to just consider v being any arbitrary constant. In the case where v is just equal to v naught, you can see how x and y are both just 2 plus sine v times cosine or sine respectively. So that's still going to be a circular helix because they both have the exact same factor of 2 plus sine v naught. Z is going to be just equal to u plus a constant. So that again is also just a helix, but with different radiuses and different vertical shifts. It may also help to try to convert that into cylindrical coordinates. You can see in cylindrical coordinates, r would equal 2 plus sine v naught. That's just a constant. So these curves always have a fixed radius away from the z-axis, and z equals u plus cosine v. Well, that means that z is going to be increasing, and that gives us a helix. Well, let's take a look and see what this looks like in Maple. So once again in Maple, I've got my with plots command here, and I've got a plot 3D command with that parameterization. Let's take a look. Maybe it's a little squashed at the moment. That looks a little better. So you can see our grid lines exist right there on the actual surface itself. If I spiral this around, you can see I've got circular cross sections. Those correspond to u equal a constant, and those circles are being rotated around as u is increasing, and they are being shifted upward as well, up the z-axis as u is increasing. Now, for the grid lines where v is a constant, you see I have helixes, and that would be if you're tracing one of these lines along the spine of this shape. And for different values of v, you see I have different radiuses. And so some of these are grid lines farther away from the z-axis, some of them are a little bit closer. So that's going to be affecting the radius of the helix. Some of them are a little higher, some of them are a little lower. That's the z component of that helix. There we are. That gives us a circular tube in the form of a helix. Now, you can play around with all kinds of interesting parametric surfaces like this, especially once you get the idea of how to take a shape, let's say in your xy plane, and simply just change that to a shape in the RZ plane and then rotate that around by 2 pi. You can make all kinds of crazy looking donuts and toruses that way. So I'll just give you a couple fun examples here. So for a neat little example here, let's start off with an asteroid. That's that interesting sine cubed cosine cubed shape with a radius of 1 in the RZ plane. So I'm using cylindrical coordinates here. We're just going to shift this to the right by 2 units along the R axis. So r is equal to 2 plus sine cubed u, where u is my parameter, and z is equal to cosine cubed u. U is a parameter between 0 and 2 pi. So if we want to try to sketch that, we're going to go 2 units to the right, we're going to draw that asteroid. Something like that. Now, to make this an interesting surface, I'm just going to take that and convert to x, y, z, Cartesian coordinates. And that's going to get me an extra parameter, theta. All right, so that gets us our x equals 2 plus sine cubed u cosine theta, y equals 2 plus sine cubed u sine theta, and z equals cosine cubed u. Now, thinking about our parameter domain, we're going to continue to let u go from 0 to 2 pi. But since we're converting from our cylindrical coordinates to Cartesian coordinates, we should also have our theta go from 0 to 2 pi. So this would be 0 to 2 pi squared. All right, well, let's see what that looks like in Maple now. So here I've got that nice looking asteroid rotated around, and it kind of looks like a torus. In fact, if I had just let that be a circle instead of an asteroid, then I would have ended up with just a perfect donut. Well, if you want to double check and see what these cross sections look like, I will just take theta, and I'll only go 3/4 of the way around to 3 pi over 2, and you can take a look and see that opening, and there is my asteroid shape just being rotated around the z-axis. Now let's do something even more crazy with that same kind of shape here. This last example will be a little bit more interesting by the fact that what I'm going to do is I'm going to take that asteroid in our ZR plane, and as we go and increase theta all the way around from 0 to 2 pi, I want to slowly rotate that shape. Now what I'm going to do here is just use a little bit of linear algebra to be able to quickly understand what r and z are going to look like if I rotate that shape. Now, I want to be careful. I want to rotate this shape around its center point. So I'm going to rotate that asteroid initially and then shift it by 2. So I'm going to set up RZ as being a vector here, and I'm going to use our nice little rotation matrix that we learned from linear algebra. And if we want to rotate counterclockwise by some angle theta, we multiply by cosine theta, sine theta, negative sine theta, cosine theta. And I'm going to apply that rotation matrix to the parametric equations for the asteroid of radius 1 centered at the origin. Now I want to be a little careful. As I go around from 0 to 2 pi, I am going to be rotating this slowly. I actually only want to complete a quarter rotation as I go from 0 to 2 pi. So in order to achieve that quarter rotation from 0 to 2 pi, I'm going to change all of these thetas to theta over 4. So that's just going to take my asteroid centered at the origin and rotate it as theta goes from 0 to 2 pi by a single quarter rotation. Now I just need to make sure that I shift that 2 units along the r-axis. So I'm just going to add the vector 2, 0. So as a result, that gets me the equation of this asteroid centered at r equals 2, z equals 0, and slowly being rotated as theta goes from 0 to 2 pi. Now I'm going to convert that back to Cartesian coordinates, and that is by taking r and multiplying by cosine theta to get our x component, taking r, multiplying by sine theta to get our y component, and we already have the z component. So it's quite complicated looking, but let's take a look at what kind of a neat little shape this ends up turning that donut into. Once again, we'll turn to maple. And here it is. So you can see that I have a very similar looking shape. The cross sections are asteroids. But I have slowly been rotating this thing as I go from theta equals 0 to theta equal 2 pi by a quarter rotation. And that means that an edge of the asteroid, as it rotates around, one of those little vertices are going to end up matching up with another vertex perfectly. That causes me to have a single edge going around all the way 4 times around this surface, leading us right back. So you can almost imagine if you had a little ball rolling along this track, it's going to roll around 4 times and come exactly back to where we started. And as a result, you can do all kinds of fun surfaces like this with interesting little rotations around the z-axis and little rotations around the center point of the cross sections. And you can make all kinds of shapes such as like the Mobius strip here. This is just taking the equation of a line, and I'm just deciding for that line to go from v equal -1 to v equals +1, and applying that same sort of rotation matrix as I rotate around, and I get a Mobius strip, a single side and a single edge. So there's lots of fun things you can do with parametric surfaces. Although they can be very difficult to visualize, having a tool like Maple is just invaluable for being able to actually rotate it and see what it looks like. But barring that, your best sort of strategy is see if you can make it kind of relate to a similar problem we've seen before, like planes or cylinders or spheres, something like that. Remember that a cylinder doesn't have to be circular. You're just looking to see that something like x and y are going to be using a single parameter, and z uses another single parameter, and you can see how maybe you could end up getting a cylinder of some kind of weird shape like that. But, if it's not a common shape, then maybe try the grid line approach. Let u be a constant, and you should get the parameterization of a curve, and hopefully you can recognize that curve. Then let v be a constant. See what you end up getting for curves in that direction. And then your grid lines now become curves on the surface, and you can try to visualize it that way. Well, we'll be doing lots more with surfaces, including finding their surface areas in another video. So I'll leave it at that for now. Thanks for watching, and I'll see you in the next video.